All right, guys, quiz should be timed out at this point. So hopefully everybody can see my whiteboard here. So what I want to do is just go back and review a few things that we talked about back in the video from last night, which hopefully everybody got a chance to look at. So the topic of that video is molar concentration or molarity. All right, so basically this has the symbol of a capital M, and what it stands for is the moles of the solute, which is what gets dissolved in the solution, per 1 liter of total solution. Okay, so it's not your volume of solvent, but it's your liters of total solution, which is your solute and the solvent together. And as we talked about in the video, we normally would do this in a volumetric flask. So that allows us, for example, to define the volume of the total solution that way. Okay, so we might do this in a 1 liter volumetric flask. So we know now that that has a volume of 1.000 liters, depending upon the precision of the vol flask. That's usually given in the problem. All right, then the other thing that we found out was that we had another use of molarity, and that was another way to get to moles. So if you look at the units of molarity, it's moles of solute per liters of solution. So if I take a certain number of liters of solution and I multiply that by the molarity, you can see that the volume units are going to cancel out, and that's going to leave me with moles of solute. Okay, so we can say that molarity times volume is going to give us the moles of the solute. Now that's useful in certain situations because that actually is a way to get us to moles. So for example, in that one of the problems, the one that had the sodium cyanide in it, that was the trick that we wanted to use. So think about volume and molarity as just another way to get to the moles of solute. I think in that problem, once you had the moles of the solute, you could use the molar mass and get directly from moles to grams. Okay, so that's that situation. So we can think about both of these as being sort of useful definitions of molarity. And we're going to use both in various problems that we do from here on out. Okay, so let's just look at a few simple examples here. So example number one here, I'll give you guys a moment or two to copy it down while I read it here, is we want to calculate the molarity of a solution that we're going to prepare by adding 98.3 milligrams of a solid, and that solid is 97.9% urea by mass. And I give you the formula of urea there. Okay, so it's a solid, but that solid is not pure. Okay, so it's urea with a little bit of impurity in it. And I'm going to dump enough of that in, the 98.3 milligrams of the solid, into enough water to make 5 milliliters of solution. So for example, I could do this in a 5 milliliter volumetric flask. Okay, and I want to know the molarity of the solution. Now, when I talk about the molarity here, I'm really talking about the molarity of the urea because that's actually my solute. All right, so how would we go about setting this up? Well, we have a few steps that we have to get to. And ultimately what we need to get is the moles of urea that we're putting in the solution. Once I've got that, I've got the volume of the solution. So moles over volume gives me molarity. Okay, so I got the volume, I just need the moles of the urea. All right, so I'm going to start out with the mass of the solid. I'm going to go way out. So I've got 98.3 milligrams of my solid. And again, identity is important here. Let's go ahead and convert that to grams while we're here, because we're going to have to do that sooner or later. Okay, so for every 1,000 milligrams of the solid, I've got 1 gram of the solid. Okay, so milligrams cancel with milligrams. And now I want to get to urea. And I'm going to use my mass percent almost as a concentration, if you will, of urea in the solid. So I know, for example, that in every 100 grams of the solid, just because I'm used to thinking about this in terms of a percent, so it's per 100 things, I'm going to have 97.9 grams of urea. Okay, so notice that grams of solid will cancel with grams of solid. So essentially, I'm just introducing a mass percent there. All right, so now I've got grams. I need to get to moles. Now I can do that because I give you in the problem a molar formula. This is actually a molecular formula of urea. It's the CONH2 taken twice. Okay, so if I know the formula of it, I can use my molar mass to get me to moles of urea. Okay, so I know that for every 1 mole of urea that I've got, I can go calculate a molar mass for this, which I did based on that formula that I gave you. And we all know how to do that, so I'm not going to take the time outside to do that. That's 60.0534, according to my periodic table. And that's grams of urea. Okay, so just a mole to gram conversion there. All right, so grams of urea will cancel with grams of urea. I've got moles of urea. So now all I got to do is divide by the volume that I've got. Okay, and I can go ahead and do that in milliliters. And I'm just going to put a 1 up here just as a placeholder because I want to divide, right? So if I took everything through at this point, if I've gotten the top, I'll get moles of urea in the numerator. I want to divide that by the volume. So that's my 5.00 mils of solution that I've got. But in order to make it a true molarity, I got to convert from milliliters to liters. So let's just go ahead and do that in one more step. So I know that for every 1,000 milliliters of my solution, I've got 1 liter of solution. Okay, so notice I'm left with moles up top. Milliliters will cancel here and here. So now notice what I've got left. I've got moles of urea in the top divided by liters of solution in the bottom. Okay, so now when I work all this out, looks like I'm going to be good to 3 sig figs. I'm going to get 0.321. And I could call that big M urea. Because remember, big M stands for molarity, okay? So I could also say that's moles of urea per liter of solution if I wanted to state it that way. So either way would be absolutely perfectly correct, depending upon what you would like to do. All right, any questions about what I did there? It's really just kind of gram to mole conversions and things of this nature that we've done before. So it's just kind of pulling it all together with a new definition. Okay, good. So let's look at another example. This one actually deals with a liquid solute. The urea one was a.
Can you please go back up, Professor?
Yeah, sure. Sure can. Which would you like to see? The whole thing?
I'm good now.
Okay, no problem. I don't mind.
I have a question.
Sure, go ahead.
The 1 liter, does it get canceled out?
It doesn't. There's nowhere to cancel it, right? Do you see any
Right.
liters elsewhere in there that we can get rid of?
No.
I don't either, but I do want to get rid of the mils there, right? Because, and the reason I converted the mils to liters is because that goes back to my definition of molarity. It's always moles of solute per liter of solution, not milliliter of solution. So again, it's adhering back to that definition that we need to use. All right, am I okay to scroll down, at least part way? I'll leave you some of the problem there to work with. I just want to have example 2 there. I'll leave the solution to example 1 there. All right, so let's look at example 2. Again, this is going to be a liquid solute instead of a solid solute. A solute can be a liquid, a solid, or a gas, really. So in this case, we want to know what the molarity of a solution is that we're going to prepare by adding 125 milliliters of methanol, or that's sometimes also known as methyl alcohol. It's got a volume of, or sorry, a formula of CH3OH, and I give you a density of it there. That's 0.792 grams per milliliter. And I'm going to make I'm going to add this to enough water to make 15 liters of solution. So again, I got my volume, right? So I've got my denominator to get to a molarity. I need my moles of my methanol. All right. So what are we going to do here? I've got a volume of the methanol I'm going to put in, but to get to moles of methanol, can I go directly from a volume of methanol to moles of methanol? Do you know of a way to do that? I don't, given what's in the problem. So why do you think density is there? What's density going to be useful for?
For finding the mass of the methanol.
Yeah, because remember what density does for us. For a given substance, it lets me move between volume and mass, right? So in this case, I gave you a volume, and it might be useful to go to a mass, because if I can convert the volume of methanol to grams of methanol, then what can I do? Where do I go from grams of methanol? Because remember what I'm trying to do. I'm trying to get to a molarity, which means I need the moles of the methanol. Can I go from grams of methanol to moles of methanol if I have a formula? Sure, that's easy. Okay, so that's why you've got the density in there. So I'm going to go ahead and scroll down. So let's go ahead and put the given in here. Looks like I've got 125.0 mils of the methanol. I'll just call it CH3OH. I'm going to go ahead and do I need to convert that to liters? No, I don't, because the density is in terms of grams per milliliter. Okay, so I know that for every 1 milliliter of CH3OH, I've got a mass of 0.792 grams of it. Okay, so notice that the milliliters will cancel with the milliliters. Okay, so now that I got the mass of it, I can use the molar mass to get me to the moles of the methanol. All right, moles are what I want in top, so I'm going to put 1 mole of CH3OH up there. And again, I know that the formula of methanol is CH3OH, so I can go to the periodic table off to the side and calculate the molar mass of it. Or in my case, I would probably just go look it up, but hey. And that turns out to be 31.0424. And that's going to be grams of CH3OH contained in 1 mole of it. Okay. So now notice that grams of methanol will cancel with grams of methanol, and I'm left with moles of methanol. Now, all I need to do is divide that by my volume, which is already in terms of liters, and that'll give me the right units for molarity. Okay, so I'll just tack that onto the end here. Again, I'll just put a 1 as my placeholder here so I know to divide. And that's going to be divided by 15.0 liters of total solution. Okay, so notice what I get. I get moles of solute, which is CH3OH, per liter of solution, and that's the appropriate unit for molarity. Looks like I'm going to be good to 3 sig figs here, because it looks like I'm limited by my volume of my solution there. So when I work this out, it turns out to be 0.206 molar. Okay, so just another way to get at molarity. In this case, utilizing a volume of a solute instead of a mass of a solute. And that's what we usually do if we have a liquid solute that we have to deal with. I'll leave this for just a second for anybody who needs to continue to copy that down or what have you. Any questions about that, guys? So again, it's kind of more of the same. You know, you can hopefully see a pattern emerging here in terms of how we work these kinds of problems. Now I've got peeking down here this next concept that I want to talk a little bit about, and it's called dilution. Okay, so this is another way to deal with molarity and concentration. So in the prior 2 examples that we had, and also with the ones that we talked about back in the video, what I had was some volume or mass of a solute that I'm going to add to some volume of solution. Okay, and I'm going to combine those to get a molarity. Now, dilution is another way of making a solution. So in this case, what I would do is I would have a stock solution. All right. So a stock solution is going to be a solution of my solute that's already made up of a known concentration. And the idea behind dilution is I want to take that stock and make it less concentrated, right? When we talk about dilution, that's what we're trying to do. We're trying to take something we're starting with as a solution and making it less concentrated. Okay. Does everybody have what they need for example 2 there? So I can scroll up. All right, good.
I had one question.
Yeah, please go.
How did you get the mass of the methanol as 31 point 0.042.
Well, hopefully I did it right. I went to the periodic table and I used the formula, right? So it's a carbon, 3 hydrogens, an oxygen, and another hydrogen. So I would have added up carbon, what, 12.01 plus 4 more from the 4 hydrogens plus a 16 for the oxygen. That should take me about there.
All right. Okay. Thanks.
Yeah, it's just a molar mass.
Okay. Thanks.
No problem. Yeah, if there's anything you're wondering about, just ask. So for dilution, again, what we're trying to do here is we're trying to use a stock solution. And a stock solution, by definition, has a known concentration, we'll say known molarity, to make a new volume of a less concentrated solution of the same solute. You actually end up doing dilutions a lot in the lab. So I'm guessing in your lab somewhere along the way, you're probably going to end up having to do some dilution calculations, then make some dilutions of a given solution from a stock that's given to you. Okay, so let's kind of just sort of draw this out, if we will. So let's say I've got a beaker here. Excuse my art here, guys. And in this beaker, I'm going to have a 1.00 molar solution of NaCl. We'll just make something simple like table salt here. Okay. And I want to make a more dilute solution out of it. So I want to take that 1 molar NaCl solution and make it a lower concentration. Okay. So what I'm going to do is I'll have another beaker over here. And what I'm going to do is I'm going to take an aliquot or a portion out of the first one, and I'm going to add it to the second one. So let's just say, for example, I'm going to use like a pipette, and I'm going to take out 10 milliliters of the original solution and then dump it into this second beaker. Now, has the concentration changed when I've done that? No, it should be the same concentration, because all I did was I took 10 milliliters of the original solution and stuck it in the second beaker. Other than that, I haven't done anything to it, right? So the concentration is the same. But now, what if to the second beaker, I add enough water to get, let's say, 100 milliliters total solution? Okay, so in other words, I'd have to add around 90 milliliters of water to the 10 milliliters that I put in to get my 100 mils of solution. But you can see what I've done here is I've increased the volume of the total solution. So now I've got 100 mils of solution in this second beaker. Okay, now have I changed the concentration of the sodium chloride now in that second beaker by adding that water?
Yes.
Oh, definitely. Yeah. Have I made it more concentrated or less concentrated?
Would it be less concentrated?
Yeah, definitely less concentrated, because I've got the same number of, I've added some fixed number of moles of solute over there in the 10 milliliter aliquot, but now I added a whole bunch more liquid to it, right? So that made it more dilute or less concentrated. Now, the way I could actually do this is just with a simple mole calculation if I wanted to. So if I think about that 10 milliliter portion that I took, all right, I could find out how many moles of sodium chloride are in that. So let's say I took my 1000 milliliters. Let's go ahead and convert it to liters, because we're going to use molarity times volume to get to moles. All right, so I know, for example, that in 1000 milliliters of the solution, I've got 1 liter. Okay, so mils cancel with mils. And now I want to multiply by the molarity. Oh, and I had a fixed molarity, right? So I had 1.00, and I'm going to rewrite my molarity as moles of NaCl per liter of my solution that I started with, okay? Because that's what molarity is. Notice what happens. Liters cancels with liters, like we said before, and I end up with moles. So what this is telling me is how many moles I'm transferring from one solution over to the next. Okay, so I've got 10 divided by 1,000 times 1, and I end up getting 0.010. It looks like we're good to 3 sig figs. We'll put another one there, moles of NaCl that I'm carrying over. Okay, so now once I get it to the other side, I'm changing its volume, aren't I?
Oh, Professor.
So if I want, yeah, go ahead.
Where did you get the 10 ml from?
The 10 mLs, see my little arrow above where I'm talking about moving a portion of one solution to the other
Yeah.
beaker? That's where the 10 mLs comes
Or
from.
where's
in other
that in the problem? Like, where's that?
There is no problem. I'm just defining that as I go. I'm telling you that I'm
okay.
taking 10 mils of the solution and moving it from one beaker to the other. So in all honesty, I'm kind of making this up as I go. All right, so but that's where that's coming from. It's that aliquot size. I'll put a little arrow to show you that where that's coming from. Okay, that's what I'm moving from the left beaker to the right beaker. And I just stated that. So now I want the molarity of what's in this other beaker. So what do I need? I need the moles of the solute divided by the volume of the solution, right? So if I want the molarity, I've got the moles. I just calculated that of NaCl I'm moving over. So I'm going to just put 0.0100 moles of NaCl. And what volume have I now put that in? What's it in now once I do the dilution? What's my new volume, in other words?
100 milliliters.
Yeah, 100 mils, right? And I'm going to go ahead and just state that as 1/10 of a liter, right? Because 100 mils is the same thing as 0.1 liters. Just skip a math step here. Okay, good. So if you calculate that out, you end up getting 0.100. And that's my molarity of my new solution, right? So notice what happened. I took a 1 molar solution in the beaker on the left, and I now diluted it down to 1/10 of a molar solution of NaCl, okay? So that's how we do it. Now, there's a shortcut you guys can use here. It's called the dilution equation, which I'm going to give you here. So you don't have to remember all of this. You can just kind of throw an equation at it, which a lot of people find a lot simpler. And it says this. Big M is molarity. We'll say the molarity of the concentrated, the little c there stands for concentrated, times the volume of the concentrated is equal to the molarity of the dilute, the little d stands for dilute, times the volume of the dilute. Okay? So you could have done this problem by just solving for the molarity of the dilute. Okay, so if I had done that, M dilute is going to equal to M concentrated times V concentrated divided by V dilute. And that's pretty much what we just did, right? The M concentrated times the V concentration is the result of that double underlined calculation I did over there. And then what did I do? I took that number and divided by the new volume, which is 0.1 liter. Okay, and that gives me the 10th molar. So it's just a fast way of getting to the same thing. Okay, and usually if you're in the lab and you need to do this quick, the dilution equation is the way you want to go. So let's just look at a real quick example using the dilution equation here. So it says how many milliliters of a 2.05 molar solution of KNO3 are needed to prepare 250 milliliters of a 0.5 molar KNO3 aqueous solution. So obviously I'm doing a dilution, right? I'm starting out with a concentrated solution of 2.05 molar, and I want to make 250 milliliters of a 0.5 molar solution of the same solute. So in other words, I'm starting with a big concentration and I want to make it small. All right, so let's think about it. I'm going to go ahead and write my dilution equation here, and let's just think about what goes in there. So it's the molarity of the concentrated times the volume of the concentrated. That's equal to the molarity of the dilute times the volume of the dilute. So let's think about what we have and what we don't have. Okay, Now, do I have the molarity of the concentrated? Yeah, I got that. I'm just going to sort of just throw some numbers here so you guys can see. That's 2.05 molar, right? That's the molarity of the concentrated part. Do I have the molarity that I want to get to for the dilute? Yeah, that's given in there as well. I know that my target molarity in my new solution is 0.500 molar. What volume do I have? Is it the volume of the concentrated or the volume of the dilute? You see a volume there. Which one does it refer to? The volume of the concentrated solution or the new dilute solution?
The new diluted solution.
Yeah, you got it. It's this guy right here. Now, here's another thing that's a nice shortcut here. Since the volume appears on both sides of the equation, I don't have to convert to liters. I can use milliliters here, okay? Because, for example, if I had two volumes and I were solving for a molarity, what would happen? Well, the units would cancel each other out. So you don't have to actually convert milliliters back to liters. You can do it and you'll get the same answer, but it's a shortcut that you don't have to do that. Another nice thing about this is that this equation works for any concentration unit. You don't have to just use molarity. You could use any other concentration like percent by mass or parts per million or whatever, just as long as the concentration unit is the same on both sides of the equation. In other words, don't mix and match them. In this case, this is fine because they're both molarities. So let's solve for V concentrated. That's what we're actually asking for in the problem. So that's the molarity of the dilute times the volume of the dilute divided by, in this case, the molarity of the concentrated. So let's go ahead and stick everything in. So I got 2.05 molar. The volume of the dilute is 250 mils. I'm just going to leave that as mils. So that's convenient. It's what I have, and it's also what I'm asking for in the problem, right? And then divide that by the molarity of the concentrated, which is 2.05 molar. Now notice what happens unit-wise. Molar cancels with molar, and I'm left with milliliters. Everybody see that? So that shows that I really don't have to worry about changing those units over. And I don't have the answer. I'm going to plug it out real quick. 2.05 on my calculator times 250 divided by 2.05. Actually, I used that twice. What did I do wrong here? I shouldn't have used the molar of the dilute. Where's the molar of the dilute? 0.5. I used the wrong one up there. Sorry, guys. I can't use the 2.05 quite twice, can I? That's going to be the 0.500. Sorry, guys. Everybody see that? I plugged the wrong thing in there. And I end up getting, looks like how many sig figs? 3 sig figs is what I need. Looks like I'm going to get about 70.0. And that's going to be what? Milliliters, right? So that tells me that I need to get 70.0 milliliters of the concentrated solution to put into my new volumetric flask. And then I would fill that to my mark at 250 mils to make my new solution. Okay, and that's usually the way we end up using the equation. We need to usually know how much of the concentrated solution I need to make a new volume of the dilute solution at a target concentration. Okay, so go ahead.
I think it's 61, not 70.
Now let me check again. I might have plugged it into my calculator wrong. That's the problem when I do this. 0.5 times 250, right? Divided by 2.05. Let's see what I get. Yeah, it does look like it. I get a 61. Sorry. 60.975. Let's write it all out. Is that the value you get? And
Yeah.
then we know we're good to how many sig figs? Looks like 3 sig figs, but now we have to what, round up? So it looks like I'm going to get what, 61.0, is that right? There we go. Yep, I think I punched something in the calculator wrong. That work for everybody?
Yeah.
Okay, perfect. All right, guys. Let's do a little Chem 101 here. We got a couple minutes left, so let's just see how far we get with this. So I'm just going to open up the practice here. It's our last one in chapter 3, which means I have to actually get stuff going for chapter 4. Okay, so see how far you guys get. And some of these are actually really easy, so you can probably get through a few of them. See, on number 1 there, you're trying to go from a volume and a molarity to moles of the solute. So that's one where we use molarity times volume, right? Another way to get moles.
In the beginning of this, you had wrote an equation down, but I couldn't get it. Can you scroll back up?
Sure. Which one is that? The very first one in my whiteboard?
Yeah.
Okay, yeah, sure can. That one?
No, go up a little bit more.
There?
No, it was the equation, not the example.
Oh, I'm sorry. For the dilution?
No, the molarity.
Oh, from Larry, way up. Okay, that's way up top. There you go. Sorry about that.
Thank you. It's fine. Thank you.
Way up at the top. Okay.
Okay, I got it. Thank you.
No problem. Yeah, I can scroll anywhere you need me to be. Not a problem. On the second one, look at that one. you're trying to get to a concentration, presumably in molarity. So what do you got? It's giving you the moles of the KOH, which is your solute. Oh, and it also gives you the volume of the solution. But what do you have to do to make the units right? You got moles and volume, but look at your units. What do you have to do to that 400 milliliters of solution?
Convert it to liters.
You sure do. Yeah. All right, so as you guys finish up, just a couple things to keep in mind for next time. You do have a new video, and we're actually starting into a new chapter. So I need to release those chapter 4 homework problems for you guys to start on. And we're going to start by looking at chemical reaction equations and how to balance them. So I think that's actually what's in the next video. So make sure you guys watch that. And that's something I think a lot of folks are familiar with. And we will pick it up from there. So be ready for 5 for 5 on Wednesday, guys. You got about 9 minutes left. So feel free to continue working on this if you like.